This battery could break every electric vehicle record we know today, not by a small margin, but by completely changing what an electric car is capable of. It can travel up to 1,000 kilometers on a single charge, then recharge in around 10 minutes. To put that into perspective, that's roughly twice the driving range of many electric vehicles on the road today. It's enough to drive from New York City to Detroit without stopping to recharge. Just a few years ago, most engineers believed a battery like this was still decades away. Some weren't convinced it would ever become commercially practical, because the technology behind it had defeated researchers for more than 40 years, not because it needed more lithium. The real challenge was something much smaller: replacing a single liquid material that has existed inside nearly every modern electric vehicle battery for more than 30 years with a solid one. A change that sounds almost unbelievably simple, yet it became one of the hardest engineering problems in modern battery science. Some of the world's biggest companies invested billions trying to solve it. Many produced impressive laboratory prototypes, but building one battery inside a research lab is one thing. Building millions that can survive freezing winters, scorching summers, is something entirely different. Over the years, dozens of companies promised that solid-state batteries were just around the corner. Every announcement sounded revolutionary. Then the deadline slipped. Production was delayed. Little by little, many experts began asking a different question: not when solid-state batteries would arrive, but whether they would ever arrive at all. Because after more than 40 years of research, nobody had managed to solve every problem at the same time. Until now, the company making this claim isn't a battery startup. It isn't a Silicon Valley giant. It's Toyota, a company that has spent decades doing something very different from many of its competitors. While much of the industry focused on making today's lithium-ion batteries a little cheaper, a little lighter, or a little faster, Toyota continued investing in what many engineers considered the ultimate battery technology: not an improved lithium-ion battery, an entirely different approach. A battery without the flammable liquid electrolyte found inside conventional lithium-ion cells. A battery capable of storing significantly more energy in nearly the same amount of space. A battery designed to charge dramatically faster while remaining safer and potentially lasting much longer. If Toyota's claims prove correct, this wouldn't simply be another step forward. It could become the biggest battery breakthrough since lithium-ion first entered commercial production more than 30 years ago. But that immediately raises an important question. If solid-state batteries are potentially so much better, why has the entire world continued building electric vehicles around lithium-ion technology for more than 3 decades? The answer is surprisingly simple. For a very long time, lithium-ion wasn't just the best battery available. It was the only chemistry capable of delivering the combination of energy density, weight, reliability, and cost needed to make modern electric vehicles possible. Before lithium-ion arrived in the early 1990s, battery-powered vehicles struggled with the same problems generation after generation. Their batteries were too heavy. They stored too little energy. Charging required hours. Driving range remained frustratingly short. Then lithium-ion changed everything. Compared to previous battery technologies, it packed dramatically more energy into a much smaller and lighter package. Suddenly, electric vehicles became practical. Manufacturers invested billions. Gigafactories appeared across the world. Mining companies expanded lithium production. Governments built national strategies around battery manufacturing. Within just a few decades, nearly the entire future of transportation had been built around one chemistry. And when one technology dominates for that long, something predictable begins to happen. Companies stop searching for completely different solutions. Instead, they spend years making the existing ones slightly better, a little more range, a little faster charging, but not revolutionary ones. Because underneath every new generation of lithium-ion batteries, the same fundamental limitations remained. They still relied on a flammable liquid electrolyte. They still lost performance in extreme temperatures. They still required significantly more time to recharge than filling a gasoline tank. And with every passing year, engineers came closer to the physical limits of what that chemistry could deliver. That is exactly why scientists never stopped chasing solid-state batteries. They weren't trying to build a slightly better battery. They were trying to build the technology that could eventually replace lithium-ion altogether. And the story of how one company believes it finally solved that challenge begins with a problem that scientists had been struggling to overcome for more than 4 decades. For decades, engineers knew exactly what they wanted to build. The problem was that nobody knew how to build it. On paper, the idea behind a solid-state battery sounds surprisingly simple. Take a conventional lithium-ion battery, remove the flammable liquid electrolyte, replace it with a solid material, and suddenly many of today's biggest limitations appear to disappear. Higher energy density, much faster charging, greater safety, longer lifespan, better performance in extreme temperatures. It almost sounds too good to be true, because it was. The reason electric vehicles still rely on liquid electrolytes isn't because engineers ignored a better solution. It's because liquid electrolytes solve one problem extraordinarily well. They allow lithium ions to move quickly between the battery's electrodes. That movement is what creates electrical current. The faster and more efficiently those ions travel, the better the battery performs. Liquids are naturally very good at allowing that movement. A solid material isn't. Scientists have spent decades searching for materials capable of conducting lithium ions almost as efficiently as a liquid while remaining chemically stable for years of daily use. Finding one turned out to be only the beginning. Imagine building a road for millions of tiny particles moving back and forth thousands of times every year. Now imagine that road constantly expanding, contracting, heating, cooling, and vibrating every time the car accelerates, brakes, or drives over a pothole. That is essentially what happens inside every battery. Even microscopic imperfections become enormous problems over time. A crack too small for the human eye to notice can interrupt the movement of lithium ions. Performance begins to decline. Charging becomes slower. Capacity starts falling. Eventually, the battery may fail completely. Then came another challenge: pressure. Unlike liquid electrolytes, solid materials cannot naturally flow into tiny gaps between battery components. Every layer inside the battery must remain in nearly perfect contact throughout its entire lifetime. If even microscopic gaps appear, electrical resistance increases, heat builds up, efficiency drops. Engineers found themselves solving problems measured in microns instead of millimeters. Many battery researchers describe this as one of the greatest manufacturing challenges the industry has ever faced. Because building a single laboratory cell is relatively straightforward, producing millions of identical batteries with microscopic precision is something entirely different. Even worse, there was another enemy hiding inside the battery: tiny metallic structures called dendrites. These needle-like formations can slowly grow through battery materials during repeated charging cycles. If they eventually reach the opposite electrode, they create an internal short circuit inside a conventional battery that can lead to overheating. Inside an experimental solid-state battery, it often destroyed years of research in seconds. Entire prototypes failed without warning. Researchers modified one material. A different problem appeared. They improved conductivity. Mechanical stability became worse. They increased energy density. Battery life decreased. Every solution seemed to create another obstacle. This is why so many companies repeatedly announced breakthroughs only to quietly postpone production a few years later. The laboratory results were often real. The challenge was manufacturing. Producing one successful battery isn't enough. An automaker needs millions. Every single one must perform almost identically. Every single one must survive freezing winters, scorching summers, rapid charging, daily commuting, and well over a decade of continuous use. A failure rate acceptable inside a research laboratory becomes catastrophic inside a vehicle factory. That is why so many ambitious projects stalled. Some startups ran out of funding before solving the manufacturing process. Others discovered that their batteries were simply too expensive to compete with lithium-ion. Several companies achieved remarkable performance, but only under laboratory conditions that could never be reproduced at industrial scale. The industry slowly became more cautious. Promises became fewer. Timelines became longer. Many experts concluded that commercially viable solid-state batteries might still be decades away. Yet one manufacturer continued investing year after year, not with flashy announcements, not with constant promises, but through thousands of patents, dedicated research facilities, and one of the largest battery development programs in the automotive industry. Instead of asking how to build the world's most impressive prototype, its engineers focused on a far more difficult question: how do you build millions of them? because solving the science would be meaningless if the battery could never leave the laboratory. And according to Toyota, that is exactly the problem it believes it has finally solved. After more than 4 decades of research, Toyota believes it is finally approaching the moment the automotive industry has been waiting for. Not because it invented the idea of a solid-state battery. Scientists have been studying the technology since the 1980s. The real breakthrough is something far less glamorous. Toyota believes it has made enough progress to begin moving the technology from the laboratory toward commercial production. That may sound like a small difference. It isn't. For years, companies around the world demonstrated impressive solid-state battery prototypes. Laboratory tests produced exciting numbers. Investors celebrated. Headlines predicted the end of lithium-ion. But when it came time to manufacture thousands or millions of batteries, the same problems kept returning. Production costs were too high. Manufacturing processes proved too complex. Battery life wasn't consistent enough, or the cells simply couldn't be produced at automotive scale. Toyota believes it has made significant progress in solving many of those challenges. According to the company, its latest solid-state battery technology could eventually deliver up to 1,000 kilometers of driving range while reducing charging time to around 10 minutes. If those figures are achieved in commercial vehicles, they would represent one of the biggest advances in electric vehicle technology since lithium-ion batteries first entered the market. Think about what that could mean in everyday life. Today, one of the biggest concerns for electric vehicle owners is planning long journeys. Drivers constantly think about remaining range. They search for charging stations. They calculate whether they can reach the next charger. Every long-distance trip requires planning. Now imagine driving nearly twice as far before needing to recharge. For many people, that could mean driving an entire week without visiting a charging station. Then consider charging itself. Today's fastest charging systems are already remarkably capable. But even under ideal conditions, most drivers still spend 20 to 40 minutes waiting. Toyota believes solid-state technology could reduce that waiting time to around 10 minutes. That's approaching the amount of time many people already spend stretching their legs, buying a coffee, or taking a short break during a road trip. Safety is another reason engineers have pursued solid-state batteries for so long. Conventional lithium-ion batteries use a flammable liquid electrolyte to transport lithium ions. Toyota's approach replaces that liquid with a solid electrolyte. Removing the liquid doesn't eliminate every possible battery failure. No battery is completely risk-free. However, a solid electrolyte has the potential to significantly reduce the risk of thermal runaway, one of the industry's biggest safety concerns. Another major advantage is energy density. A higher energy density allows manufacturers to store more electricity within roughly the same battery volume. Automakers then have two choices: keep the battery pack roughly the same size and dramatically increase driving range, or maintain today's range while reducing battery size and vehicle weight. A lighter vehicle improves far more than efficiency. It can improve acceleration, handling, braking, tire wear, even overall energy consumption. Toyota also expects solid-state batteries to offer improved durability over many charging cycles, although that will ultimately need to be proven under real-world conditions once commercial vehicles reach customers. And that brings us to perhaps the most important point of this entire story. Despite all the excitement, Toyota is not yet mass-producing these batteries. The company has stated that its goal is to begin commercializing the technology around 2027 to 2028. That means one enormous challenge still remains: scaling years of laboratory research into a manufacturing process capable of producing hundreds of thousands and eventually millions of batteries with consistent quality. History has shown that this is where many promising technologies struggle. A successful prototype does not automatically become a successful product. Toyota understands that better than most companies. That is why its engineers have spent years developing not only the battery itself, but also the manufacturing techniques needed to produce it reliably and economically. If the company succeeds, the impact could reach far beyond Toyota's own vehicles, because the moment one automaker proves that solid-state batteries can be manufactured at scale, every major competitor will have to respond. And that could trigger the biggest battery race the automotive industry has seen since lithium-ion first transformed electric vehicles more than 30 years ago. So, does this mean lithium-ion batteries are about to disappear? Probably not. History rarely works that way. New technologies don't replace old ones overnight. overnight. They earn their place one application at a time. When digital cameras first appeared, film didn't vanish. When LED lights entered the market, traditional bulbs continued to exist for years. The same will likely happen with electric vehicle batteries. Lithium-ion technology has spent more than 3 decades becoming one of the most refined energy storage systems ever created. Manufacturers know how to build it. Supply chains already exist. Factories are operating around the clock. Costs continue to fall every year. For many affordable electric vehicles, lithium-ion batteries will almost certainly remain the most practical solution for years to come. But history also shows something else. Every major technological revolution begins at the high end. The first flat-screen televisions were incredibly expensive. The first smartphones were luxury products. The first electric vehicles were affordable only to a small number of buyers. As manufacturing improved, prices fell. Eventually, technologies that once seemed extraordinary became ordinary. Solid-state batteries could follow exactly the same path. If Toyota successfully brings them into mass production, the company's first vehicles will almost certainly be premium models. Not because Toyota wants to limit the technology, but because every new manufacturing process is expensive in its early years. Production volumes are low, factories are still learning, costs remain high. That is completely normal. As production scales, manufacturing becomes more efficient. Costs begin to fall. More vehicles receive the technology. Eventually, what was once exclusive becomes available to millions of drivers. But perhaps the biggest impact won't be Toyota itself. It will be the reaction of everyone else. Imagine one manufacturer suddenly offering electric vehicles capable of driving nearly twice as far while charging in a fraction of the time. No competitor could afford to ignore that. Tesla would accelerate its own battery research. CATL would increase investment in next-generation cells. Samsung SDI, Panasonic, LG Energy Solution, BYD, and other battery manufacturers would race to commercialize competing technologies. Automakers around the world would be forced to respond, because in the automotive industry, standing still has never been an option. That competition could trigger the next great battery race, not one focused on making lithium-ion slightly better, but on building the technology that eventually succeeds it. Of course, one important question still remains. Will Toyota actually deliver? That is something nobody can answer today. The company has announced ambitious targets before. Developing a breakthrough battery inside a laboratory is one challenge. Building millions of reliable batteries every year is another entirely. Mass production has defeated many promising technologies before, and until solid-state batteries begin appearing in production vehicles, a degree of skepticism is completely reasonable. But this time feels different. Not because of marketing, not because of exciting headlines, but because Toyota has spent years speaking cautiously about this technology. Rather than promising immediate production, the company has focused on solving manufacturing challenges, improving durability, and preparing for commercialization around 2027 to 2028. That measured approach has given many industry observers greater confidence that this project has progressed far beyond a simple laboratory demonstration. Whether Toyota becomes the first company to mass-produce solid-state batteries or not, one thing is becoming increasingly clear. The next chapter of electric vehicles will not be written simply by building larger batteries. It will be written by building better ones. For more than 30 years, lithium-ion batteries transformed transportation and made modern electric vehicles possible. Solid-state technology may now represent the next major step in that evolution, not by replacing lithium-ion overnight, but by gradually overcoming the limitations engineers have been trying to solve for decades. Longer range, faster charging, greater safety, higher efficiency. If those goals become reality, the electric vehicles of the next decade may look very different from the ones we drive today. And years from now, we may look back on this moment as the point when the industry stopped asking whether solid-state batteries would ever become real and started asking how quickly they would change the world.